Okay, you guys in the back, I just want to make sure you're aware that we are recording. Any chit chat was going to be preserved on the internet there, so I would suggest that we try and stay focused on the topic, just so we all look like respectable people that are interested in cybersecurity. All right, let's see. Does Twitch look good? Twitch, today I did show up 20 minutes early. I can see your chat. Doesn't mean that I'm going to crush it, though, as far as responding to you. Okay, today is 9/2. We are, I think, on week 3 here. And we're about to go into reverse engineering. It doesn't mean I'm going to talk about reverse engineering today. It's whatever day I woke up. Okay? And it turns out time runs on my schedule. If you've seen me on the Discord, you know that I just don't sleep. So, memes. Teaching the same course every year, how do I make it fun for me? The answer is yes. Make some memes. We can hopefully get a good chuckle or two as we move through this stuff. It also gives you guys extra credit, right? It's a good way of doing things. So, hopefully over the past week, you messed around with GDB. Hopefully you found GDB to be a useful tool. All right, the foundation for apparently someone, at least, solving levels 5 through 14 and beyond was throw GDB at it, and I throw an int3 in my shellcode. This lets me see what's going on, start stepping through it, thinking about how things work. I think it's a great way to work. Solid meme. The other day that I said on Thursday, I showed how to set up Jeff. Jeff is that GDB plugin that gives us all that info. Jeff is amazing. If you're using pwn.debug, that's your choice. Jeff is the correct one. So, we also made strategies for success, some like tricks, and these are challenge specific. Depending upon how far you got through the module, you'll know what they're actually talking about. And if you didn't get through the module, this is probably good advice to consider on the problem you're dealing with. So we showed on Thursday symlinks, what they are and how they can be beneficial. Good being. One of the challenges says you can't use syscalls, right? You can't have the syscall instruction. So what happens if instead, it turns out here a syscall, I think has F at the end, it's OF, it's like OF, O5, based on this meme. We can have something that is not a syscall and then modify it in place. And as the CPU processes, that would change the assembly. So we could have self-modifying shellcode. That could mean. This does require that region of memory to be readable, writable, and executable, which is not necessarily the case in general, right? We did this for these challenges. There's a challenge where the shellcode the challenge would modify your shellcode. And it would say, all right, you get 10 bytes, and then every other 10 bytes, we're going to mess it up and make it so this breaks. What was a strategy we could employ to address that problem? We could jump over the mess that the challenge is making. So we'd write a couple instructions, we'd hop over this mess, we'd start executing some things we're interested in, and repeat it, very much like this pole vaulter, solid meme. And then some people realized for the very kind of tail end of the challenges, you get very constrained as far as the number of bytes that you can use. And one of the great tricks there is to deploy a two-stage shellcode, where the first one just calls read, and the second one can basically do whatever it wants. Solid meme. Moving on to the kind of memory corruption side of things. I didn't talk about it in class, was in the videos. People got to learn what a canary is. Does anyone here want to tell me what a canary is? We got one in the back?
Yeah, it's a value on the stack that basically protects the end of a buffer so that if this canary gets overridden, the program will automatically check what the value of the canary is. If it's wrong, it'll stop.
Okay, so the canary is kind of this magic value that exists on the stack. And so in the event we are doing some type of memory corruption buffer overflow, we would overwrite this magic canary value. And when a function returns, it checks the canary to see if it's been modified. And if it has, it blows up and says stack smashing detected, and it causes problems and grief for us. So canaries were something you probably didn't see in 365, but we got to mess around with them a bit right here. We also dealt with, this is not a canary meme, and so the canary always ends in the least significant byte with a null byte, and that prevents people from overreading into that canary. There's rhyme and reason for that. You can take advantage of exactly that in some of the memory corruption challenges. Generically, the canary protects the saved RBP and saved RIP. You can find other values on the other side of the canary as well, but generally speaking, it will be those two. Some people have a burning passion and love for canaries, right? That's perfectly fine as well. Oh, this one here for memory errors level 9 is not about canaries. Does anyone know what it is about? Let's go right here.
The randomized nibble.
Okay.
Yeah.
The randomized nibble. So another thing that you may not have dealt with in 365 is something that's called ASLR, and then how that relates to something that's called PIE. These two mechanisms are different, but they functionally accomplish the same thing. And that is memory addresses will suddenly start to be randomized. The page that your data is getting mapped to is randomized. So now I can't just know before I start the challenge where is something in memory, because these locations change every time you run it. One of the strategies that was employed to kind of solve these challenges was to brute force it. So we could have an exploit that did a partial overwrite. Now a byte is 2 nibbles. The first 3 nibbles are constant. That means we have 1 nibble that is randomly generated that we are guessing. That can be any value from 0 to F, so it's 1 in 16. So we would have to run this on average 16 times before we would see success. Some of you, I'm sure, if you did this, were unlucky and had to run it 30, 40 times. This is where having confidence in what you were doing and looking at it in GDB is important. Because I can't just run it and assume, oh, it didn't work, I did something wrong. You have to understand the concepts at play here. And so here we have somebody that's going to just keep up entering until it works, where someone else could give up early. Solid meme.
What does that even do? Up enter.
Up enter, so if you're on a terminal, you hit up, it'll give you the previous command that was ran, enter would run it. I could then hit up, get the previous command, and then hit enter and run it. Now, my personal suggestion is you can discover this amazing thing called a for loop, but if that's your jam, have at it. I'm not teaching, basic computer science concepts here. I included it twice, so we saw that. Right? Alternatively, we could do the up enter, and then if you did brute force it, like you did something silly, because there's some of the later memory corruption challenges, you could actually leak out the canary and then know what it is to overwrite. If you are just writing some insane for loop to brute force something, if you got the flag, you solved the challenge. Right? You may not have used an optimal approach. Flag is flag, you get the points. I don't really care how you did it. But I'll certainly try and guide you to the most efficient path. Grades. Now, and every time we finish a module, I try and give kind of a status update here. As far as what are grades, I normally don't have so many grade-related memes, but you guys did a good job of expressing how you felt grades were doing. And as I go through the next couple slides here with some actual data on them, I don't think these memes are that far off. For some of the people that just try to tackle this module, the course is probably over for you. All right? Simply because this content builds up on itself. You're welcome to follow along, but we are not going to push the deadline. We're not going to delay what we're talking about. At the beginning, first 2 lectures, I wasn't making stuff up when I said this is going to move fast and be the hardest course that you probably take in your undergrad. So if you were betting on that, you made the wrong bet. For those of us that weren't familiar with shellcoding, this was something brand new, and you happen to solve shellcoding level 4 at the very end. Thank you for that, Twitch. I try and be motivational. Awesome, right? Hopefully you learned a lot getting there. Right? But from a course progression standpoint, I can't teach assembly over the course of this semester. We're teaching a number of concepts that kind of depend on that. And so I found these very, very amusing, but at the same time, there's kind of a sad undertone there. Now, part of the reason that this module was so hard for people is this right here. There are people who took 365 in 2022. There are people who took 365 in the spring. And over the summer, we just kind of forgot about it. I understand and I empathize. That's why we did kind of a trial by fire here. All right. Hopefully, some of those neurons started firing. You put in the time, you busted your butt, and all of a sudden you're like, oh, I know how to read some assembly now. I have an idea of how to use a debugger. I had to learn these skills to progress. So hopefully, those skills, were made up this module. So then when we use them again, you already have them, and we aren't spending time kind of refreshing stuff that we knew at one point. So one of the things that I like to look at, this is not grades, for the record, this is solve rate. So every line is some student that made at least one solve, right? And the time that you did it. And so this is from when the module launched to, I think this is like earlier today. I pulled this earlier today. And what I'm interested in, there's a lot of lines here. And so I'll improve this going later for like next week or next module. There's a couple things that I look for when I look at solve rates. It's where did people start, okay? But there is an interesting kind of cluster over here from Sunday, Monday, right? I understand if you started Saturday. How many slides did I say start early, right? I don't manage your time, but I can certainly take a look and see how you chose to use yours. And that helps me know, okay, was it that everyone started on day 1 or day 2 and we just like brick walled at 7 solves, right? There was just this challenge that was just super hard. I would see some type of pattern here. Now, this is a bit noisier because there's a number of people in the class, and so I'll try and like compress this or average this to show trends next time you see this. But there certainly were people that started late. We can all tell ourselves that we're going to do better next time. I've taught a number of these courses. It will happen again. Grade distribution. This is what you're actually here for. So we see kind of this like U shape, right? Which makes a bit of sense. Now, this isn't everyone that is registered in the class because this only shows people that have linked their Discord, right? I'm assuming those that still haven't linked their Discord are on the left side of this chart and hopefully are pursuing other opportunities. It's a good thing that we don't see anyone right here between 0.4 and 0.5 because that would mean that you did enough work to just not hit the checkpoint. So people either didn't hit the checkpoint and just phoned it in. So this is 0 to 10%. That's 30 some odd people. So that means they solved like 2 or 3 challenges. And then over here we see there's about 30 people that solved everything. I don't hate this distribution. All right. You can disagree with me here, but I would assume these people are considering what other things they could do. Or they're like, hey, I know I messed up because I started on Monday and it turns out that was a mistake. This was actually hard stuff. So they will either fall off of the grade distribution or they will drastically change how they're going to function going forward. Another way of kind of looking at this, if I just average everyone that is registered for the course for that first module, it's 54%. But keep in mind that 30, 40 of that are zeros. Literally did nothing. And so if we assume that those people have just simply decided they're not going to try and pursue the class, then we would have a class grade of about a 64. Now remember, this is not with extra credit. So if you got all of the extra credit throughout the semester and you completed 64%, you add 13 on there, that'd be a 77. That'd be like mid-high C. Okay? So keep that in context. Now, this was just ignoring people that solved nothing. If I ignore people that solved less than 3, so that's roughly that entire far left 10% side, okay? I solved the first one and just realized this was a brick wall. Then the class average is a 77.73%. And so what we're seeing here is a pretty clear division on people that have the prerequisite knowledge, started early, moved through stuff, and then people that didn't. just want to be transparent about how I'm interpreting this data. I don't think I'm far off. If you think I am, I'm more than happy to hear your take after class. But as a whole, that is very much how it reads to me. Now, if you are struggling in the course, we do have the TA office hours Monday, Wednesday, Friday. Everything I've heard from anyone that has talked with the TAs, they've said it's amazing. They've gotten them unstuck. They have spent time telling them what's going wrong. I dropped by one of them in like after hours, is whoever's still hanging out, and tried to help people as well. If we're not streamed, I'm more than happy to try and help you with exactly what you're stuck on. I've also been pretty available on the Discord. I don't think anyone would argue that I've been not accessible if you are stuck or had a question. And again, you can post memes, get that extra credit. Keep that in mind when you're looking at these numbers. Logistics. With that grade kind of discussion brought up, the drop deadline at ASU is tomorrow. So, you are free to make whatever choice you think is right for you. If you are on the far left-hand side of this distribution, I don't know that it will result in a positive outcome grade-wise at the end of the semester, because we are going to continue moving at a fairly rapid pace. And the concepts and things that may have been missed here are going to be used again and again and again. So we won't drastically change from what you experienced this past week. Now, this next module is 2 weeks, which means the checkpoint is 1 week, and then you have another week to work on it. The topic that we're going to talk about is reverse engineering. Typically, this is one of the most difficult modules that people run into, okay? I'm just telling you so you know if I'm just brick walling this, yeah, this is one of the harder ones. The easier ones are the ones that are scheduled 1 week on the schedule. I didn't have a schedule on the slide deck. But if it's 2 weeks, it's 2 weeks for a reason, okay? 36% of people that registered for this course on day one have dropped the course. Now, I said in my initial two syllabus talks that in general, this course has a 40 to 60% drop rate, right? We're approaching that. And I think as we hit the drop deadline, we will cross over that 40% threshold. So I was not making this up. I encourage you to make the decision that's right for you. Because if you decide to stay, what you will be doing for the remainder of this semester, very much so, is working on home college challenges, working on these assignments. So just same thing reiterated. All right, Advanced Reverse Engineering is going to be launching tonight at 6 p.m. That's already set up. I have not added anything to this module. I know initially I said I was going to. I'm holding off on that for right now to kind of see how things play out. Because this is actually shorter than what this module is. This module that you were getting at 6 p.m. is actually like half the size of what previous CSE466 students have gotten. The first half is what was taught in 365. And in that case, CSE365, if you didn't take it, your reverse engineering simple crack me's, so control flow starts at main, and then it's pretty much a straight line. All of the functions are embedded. Or not embedded, but in line. And so it's a pretty easy thing to reverse engineer. And then the second half of the kind of traditional reverse engineering module is a more complicated program that has many functions that call each other and has a lot more complicated control flow. I'm still on the fence on whether or not I'm going to add more stuff. If I do add stuff, the intention is not to make it drastically more difficult, but it's to complement it with some additional topics that currently aren't touched in the reverse engineering. I'm kind of having a bit of a back and forth with some other people on whether or not that would be beneficial for you or not, just as something else to explore instead of these, I think, 24 challenges that are just a straight line of increasing like difficulty and complexity. I mentioned I'm going to try into office hours. I have submitted the room request. I'm shooting for something over in BYENG. at noon on Friday. I haven't gotten a response back yet. When I know, you'll know. Demo plans. So, does anyone have any questions about something from Module 1, something I was stuck on?
Yeah, I don't know how to use backdoor. What is its purpose? Like, there is a backdoor that I saw.
Okay, so the question for Twitch is, I saw some of these challenges have this back door. What is that? How does that kind of fit in here? Why? How do I use it? Why does it matter? Yeah. Does anyone have anything else? Like 2 things that I kind of expected to be asked was ASLR, PIE. How do I reason about it? Did anyone have confusion with those? Got a couple.
It's kind of related to ASLR.
Okay.
Actually, it has to do with the counter variable in problems 9 and 10. We're
Okay.
able to overwrite the counter.
So that's a hard one for me to demo.
Okay.
I'm happy to talk about it offline.
Okay.
And then let me see what Twitch says. Twitch says, "What the heck is Yon 85?" Yeah, that's this next one. So that is something you're going to become very intimately acquainted with. Because I said that the second half of the reverse engineering content that exists on pwn.college has a more complicated program that has other functions that call functions, and we have to navigate something that isn't just a straight line while using our debugging tools. The vehicle for this is something that's called Yon 85. Yon 85 is a made-up CPU architecture, and the base understanding of what these programs are is it's an emulator. So we have a made-up architecture that we're not going to describe to you that has its own instruction set and its own implementation. And all of these programs are going to run code or take code that is written in this made-up language called Yon 85. So you will be reverse engineering something in x86 that is a program that is an implementation that runs Yon 85. May not make sense now. It will make sense come Thursday. Yes?
Does that mean we can still use like the classical reverse engineering software? Or
The question is, does that mean we can still use classical reverse engineering software?
like IDA anger management?
Like in the examples given, or IDA, anger management, I'm going to throw in GDB there, right? Can I use tools I'm familiar with? The answer is yes. You can use those tools, and you will need to use those tools. The reverse engineering is a very hard thing to teach. And the reason for that is I can explain to you what ASLR is. I can explain to you what PIE is. I can show you in GDB and dump out memory and be like, this is how this works. The act of reverse engineering is using those tools to look at something you don't understand and figuring it out. And so while I want to be as helpful as I can, a lot of questions are going to be, what does this do? Or I don't understand what I'm looking at. And the response is going to be something similar to reverse engineer it, because that is the act of reverse engineering. Okay? I'm more than happy to provide tips and techniques and run through some things, but this is a lot harder topic for me to tell you, like, this is what is occurring, because that is what you're supposed to be figuring out. So does anyone know what an emulator is? In the back.
It's just software that is used to run programs that are not usually supposed to run on a specific machine. So our programs are any kind of instruction set.
Okay, so the answer, my understanding of it, was it's a program that is written to run like programs or other instructions, like instruction sets that aren't meant for the native machine. And that's a loose approximation, or a pretty good off the hip explanation. So I'm going to look for. I don't know that this is the exact repo I'm going to use, but there is an emulator called 8086 Tiny. All right. The 8086 is a CPU that kind of is the precursor to our 32-bit CPUs. It's the precursor to our 64-bit CPUs. that we have today. There's a lot of history and backwards compatibility reasons for why things are the way they are in modern CPUs. How big this entire emulator is written in one C file? How big do you think this C file is? How many lines of code? We'll include white space. Just how big is this file? Take a guess.
5,000.
5,000. Anyone else? What do we got?
10,000 to 50,000.
10,000 to 50,000. Okay, so we're definitely somewhere in five figures, right? That's what we're thinking.
200.
Close. Like 200, you would have won the Price is Right. The answer, including white space, is 723. Okay. Now, I'm not telling you, because I don't know, how many lines of code the Yan85 emulation layer is. But it's not that many lines of C to implement something that is an emulator. Now, one of the things that's important in reverse engineering is kind of thinking, how would I implement something if I had to accomplish this task? An emulator is really like what you envision on physical hardware being implemented in software. What do you think these are? Well, it says right there. They're registers. Just like how you've learned x86, well, we implement the concept of registers in software. If Yan85 is an emulator for a made-up architecture, do you think it has registers somewhere in memory? The answer is yes. In an emulator, we have to have some concept of what the memory space, see if I can find her here, looks like. We have to have some idea of what are the instructions that we're going to run. You're going to find very similar things in these Yan85 binaries that you're reverse engineering in the next module. And they're going to have very similar patterns to what you see here. Yan85 is actually also written to emulate the 8086. So there's going to be a lot of similarities here. My plan for Thursday is to compile this, which I have a compiled version, but open it up in IDA, open it up in GDP, open it up in Binary Ninja, see what this looks like. I'm going to start working on this and reasoning about what I see in a different emulator. Hopefully, the things that I find as I work through this, which I haven't done, like we'll do it live and see what happens, will map to what you see when you work on these Yan85 challenges, because it's going to be a very similar design. All right, now to circle back, I didn't write this down. Okay, I know there was a question about saved RIP. There was a question about saved RIP. How do I find that in GDB?
RSI is good to RIP. The 14th challenge. 6 bytes.
Oh, you want to know the trick there?
How to make RSI equal to RIP?
So that's your mistake. I spent so long. I don't know if you were the one I was talking to. The very last shell coding challenge says you only get 6 bytes of input. And the trick here is to do, as one of these memes say, two-stage shell code. Right? So you're going to call read. And one of the problems there is I need to set RSI. I don't know what RSI is, but you need RSI to roughly point to RIP, right? I don't want to pull it up because then people will exactly copy what I do here on stream. But somewhere in one of those registers, if you just throw in an int3 and then break and take a look at it, somewhere in there is a memory address that is remarkably close.
Yes, there is, but it is previous to RIP.
Okay, so the statement for Twitch here is, but that location is before in memory. And that means we're just broken, right? How many bytes are you allowed to write in your stage 2?
I'm struggling with stage 1.
But you were able to call read, and you said...
Yes, but I couldn't get the file name, like the buffer where I would put my step code.
So, okay, but you saw this pointer, right? You had 6 bytes. So you could, I don't want to say it on stream, but you could cleverly decide, find a way that was definitely mentioned in my office hours when I was kind of playing around with different ways to move things. I want to say I touched on it in class. Just different. How do we move stuff around and try and do it in with less bytes, right? So somehow don't spoil it. Otherwise, I have to take down this video, sir, and then you learn nothing, right? If you refer to it in the future. Somehow we could move that memory address to the location that I'm interested in, and you are definitely not bound to a small number of bytes, right? So if I was, let's see, what is this guy? Oh, this is a shellcode runner. Okay, so I want this. This was the example binary I had that I did the memory corruption video on, right? If we open this up in GDB, we run it. Right now, where is the program? What is the program doing? It says, what is your name? It's blocked. It's blocked on read. I can Control C. I am now inside the read call. I'm going to Finny. And then we'll just give it some A's. That's a good time. All right. If we take a look at RSI, that is where my A's are located, right? So somehow I have this read ability at this location. If I examine, we'll say 20 giant hex at RSI, is it a problem if I'm trying to parallel here? I can read to here. What if my rip's over here? Is that a problem? And why or why not? If I can start controlling data up here, but rip is pointing down here, can I get to here? I just write more. So if you were able to get that pointer to be not exactly equal to rip, but nearby, right? So somewhere a little bit before it, maybe even a long ways before it. I think that one lets you write 10,000, 20,000 bytes, if I remember. It's some insane number, right? So if that pointer was just like anywhere before here, we could just send a huge payload and we'll get where we're going. And you could map it out and say, okay, from here to here is, what do I got? 16, 32, 64. I stopped mathing at 64. 80, 96. All right, I have 96 padding bytes before that location. If you wanted to math it, that's totally fine. And that's a good thing to do, right? If you want to be precise in your exploit. What else could I have done? If I just don't want to do the math. We did it in the earlier shell coding levels. Well, we could set a bunch of A's, but if we, what happens when RIP looks at A? Is it going to be happy? No, it's going to blow up. What else could we do? We could use that no-op. We could employ a NOP sled. I don't have to know how far this is. I know it's less than 1,000. Here's 1,000 NOPs. Let it cruise on down. It'll get to the end. Because NOP is a great instruction. It's 1 byte, so I don't have to care about how it's lined up here. And it's not going to change anything. So we just make this slide, and the RIP goes whee all the way down to the end. And then at the end of that slide, we put whatever we want to do. Right? You could have done that. There is a super secret 5-byte payload that doesn't use 2-stage, but I don't know what it is. Let's see what else. What do I got coming out of here on Twitch? Anything meaningful? No. Okay. How do I'll just show you. Checksec is kind of this generic command to get an idea of what mitigations a binary is compiled with. I just did this at GDB, but we could do the same thing on a binary on the terminal. It's going to tell me RELRA, which we haven't talked about. Is there a stack canary in this binary? NX, is the stack executable? And then is it compiled with PIE? Right? These are things that we want to know because they influence what we're going to do when we're working on this. Now, since this doesn't have a canary, I think that's kind of lame for me to answer the how do I know where saved rip is. So let's debug cat. All right, cat's a pretty simple program, right? We can do the same trick. I'm now inside read. I'm going to finny. I don't know if this is going to have a canary. We're going to find out. Info frame is the magic GDB command that we'd be interested in. This tells me where in memory are these saved registers. Now, normally, for most of the challenges, what you'll see here is RBP at something and then RIP at something. That is not telling you what the saved rip is. It is telling you where in memory it is. So if I were to just copy that and then say examine the giant hex at that location, that is the saved rip. Now, if this has a canary, I should be able to see it. I'm going to say, show me 20 giant hex at wherever saved rip is minus, I don't know. Don't see anything that looks like a canary there. How would I know what I'm looking for when I'm just kind of dumping out memory? What do we know about a canary? It was on one of the memes. Right, the least significant byte is always a 0. So one of the things that I don't believe was mentioned in the slides, but is relevant for this precise moment, is not every function has a canary. It turns out compilers are somewhat smart. And they recognize where there are, so there's no canary in this function that I happen to be in. But they recognize where there is the need for a canary, right? Are we reading in input onto our stack frame? If there is, then we'll have this canary check. I said there's no canary here. How do I know that? Well, I'm looking at what's going on right before the ret. I just dumped out a bunch of instructions here at RIP until I saw a ret, and I'm like, okay, that's the end of this thing. If there was a canary, we would see the check somewhere right here. Right? The canary is checked. Oh, I remember. The back door. This is the important part, why the back door matters. Let me find a binary that does have.
And that command is stack check, right?
I'm sorry, which command?
Sorry, the one that would be checking for the canary, if you were looking
here. The question was what was the command that I ran to tell me what's going on with the binary? What mitigations? It's check sec CHECK SEC. And that gives me this output. You can run the same command in GDB, and it should give you a similar output.
I was saying the check stack. When you're looking to see if it has a canary, here, you said there's a command where it would be checking. Yeah,
so I'm gonna break my own rules here. I'm gonna grab one of the challenge binaries, but I'm not actually solving it. Right? I'm just using it as a stand-in here so we can see something with the canary. 10 probably has a canary. Right? Seems reasonable. So otherwise, I'd grab random Linux bins, and we'd eventually find one, but this is probably quicker. We run checksec on it. No canary. See, these are super
9 has one.
Super easy.
That's so true.
That's fair. That's fair.
Let's go to the drill.
All right. Let's see. 9 challenge.
I think you want to be in memory errors.
Oh, you got me there. See? Good call. I do bonehead things too, guys. I still haven't looked back at my office hours and figured out why I couldn't shift left or shift right bit shift to 0. I imagine I was shifting one register and then printing out another. Okay, there we go. So this has a canary. So if we run this guy, it asks for a payload size, then it asks for a payload. I'm going to do that same trick here. And if we did info frame, we see saved RBP and saved RIP. So most of the challenges here, there are not extra registers that need to get saved, like I did with, we saw with bin cat. And this is typically what you'll see. Now, if this is where saved RBP is, we could examine like 20 giant hex at that location, and we'll go like 20 behind it. Do you see something that looks like a canary there? Okay, yes. So we see something over here that we kind of immediately identify. Hey, this is a weird looking value, because this 5.5 pattern tends to be pointing to something that's executable, something in like the text section, if you're debugging a binary. Where 7FF, this is more than likely like a stack pointer, or a pointer to some piece of memory. But this right here has a very strange look to it, and it has that least significant byte as 0. So we found our canary. Where was it? Well, our saved RBP was A500. Here's our A500. It was directly behind our saved RBP. So we could use, and as you saw with cat when I pulled it up, there can be more registers being saved. There can be more data there, but a general like loose rule of thumb is that it will be located directly behind the saved RBP that you can get from info frame. And that's how you can locate your canary or locate where your saved return address is. So I'm just on the other side of read right now. If I were to print RSI, I get A490, and we see that saved RIP is at this location here. So I could print as a decimal 1 minus the other. And I'm not saying that we can do that here because there is a canary. But if I was interested in what is that distance, it's 112 bytes. And so that's how we can kind of reason about where things are located in memory if we wanted to do that. The other thing that was asked here is, how did I know that there was no canary when I was just dumping out assembly instructions? And what we saw here is I said, I would look at what's going on right before the ret. And what we see here, this does have a canary, and so we have this call to stack check fail. What's actually happening here, the pattern that you'll see, is this right here is grabbing the canary off of the stack and putting into RCX. Now, the program has another copy of the canary located at this, we're just going to hand wave this away, this magic location, FS hex 28. And then we're going to XOR it. So if it's the exact same thing, that'll be 0. So then we jump to leave and ret if this XORed to 0. If it didn't XOR to 0, we go into this call to stack check fail. We blew up. That's where you get your error message. So why is the backdoor useful? Was the question. Well, what does the backdoor do?
Start the challenge again, call the same function again.
One of the comments from Twitch is I thought it was GS hex 28. So that's there's reasons. Depending on what you're looking at, it can be one or the other. Not important for today. So the statement for what does the backdoor do is it calls the function again. It calls itself recursively. Is that accurate? Okay. When is the canary, just based upon what I've already shown, when is the canary checked and it blows up? Right. On function return at the end. Now, I don't know that this has a backdoor. This is some random challenge. But hypothetically here, I could make this call itself and recurse. If it calls and recurses, did we check if the canary is overwritten at that point? No, we recursed.
So that is after, that is inside the.
So this I believe is a function called challenge. Yes. So main for this particular binary, right? There's a main function. main calls challenge, and that is where I am located.
Where is stack check failed function?
This is at the end of challenge. So if I disassemble challenge, it's going to overflow the screen there, but this is the end of the challenge function, right? So when the challenge function returns is when that canary is checked. If instead of returning, we recursed and called challenge again, did these instructions get executed? No. What that means is that one could mess it up and then recurse. They haven't caught me yet. I could mess it up. I could recurse. Ha ha, you still haven't caught me. And we could do that until I have all of my information that I need. Now, then once I have my information, I can get past the canary or overwrite saved rip or whatever it is I'm trying to do, because I have leaked out information or done something that I wasn't supposed to and recursed, so I didn't immediately blow up. I'm going to blow up. Like at some point, these functions are going to return, and it's all just going to fall over, right? The house of cards is going to tumble. But if I can get what I want done before then, do I care? The answer is no. So what does the backdoor let you do? Well, if I had a buffer overflow and I somehow messed up the canary, if I recursed, I don't immediately get caught. Right? That is the baseline of what that gives you.
But if you mess up, how do you know you mess up the canary unless you check it?
The question is, how do I know I messed up the canary unless I checked it? So I don't know if this has a... for this, I'm going to have to Python you. But yeah, so if you overwrote it, you get a stack smash error, right? When it's checked. Right? Now, how do you know if you overwrote it and it hasn't returned and told you? Well, you have to use something like GDB or a cyclic value. You have to use some other technique to figure out what the distance is and what you're trying to do. You strategize ahead of time, right? The distance between any 2 points on the stack is a constant value. The addresses themselves may randomize, but the distance from the top of the stack frame to the bottom of the stack frame is a known constant at compile time. There's like a slight asterisk there, but for our purposes, we can say yes, that is the case. As is the case with most things, right? There's always an exception to a rule. But if I have two things that are in a stack frame, two variables, that is hard-coded. That's why we can obtain the distance between those points statically using something like IDA or object dump and just do some math, right? Because that's a fixed distance between the, you're shaking your head no. Oh, okay, no, I want, no, like if you're like, man, you are so wrong. Like I want to know what you're thinking so we can either, make a fool of me or get us all on the same page.
In my country, this means yes. This the nodding like.
Okay, good. Culture difference?
Yeah. I'm
Okay.
understanding, yeah. Sorry,
Okay. No, I apologize then.
No, it's all right.
Okay.
It's
But does that make sense what we get from having that backdoor?
I'm still a little bit confused. Yeah, I know. Like, if you know the distance, you can poke it and get it back. You can print the value at that distance, but you can do it only in GDB, which doesn't allow you to get the flag.
Okay, so the statement was I can do that in GDB, right? I could print this like I did a little bit ago. I don't know if it's still here, but I printed RSI and I looked at that, saved RBP, and I want to say I found a distance of 120, right? And I did that. That doesn't get me the flag. And you're correct. I can't get the flag if I'm running inside of GDB. That was 112, right? But I found this 112 number using GDB. Yeah? If I were to run this without GDB, is this fact still true?
Yes.
Yes.
I hope so. Yeah, yesterday I had like something I did in GDB. The offset didn't match, and I don't know if I.
So it's very easy to get things mixed up, right? Especially if you're using GDB like this, where I am doing this dynamically, did I copy the right pointer? Did I copy the wrong pointer? You can certainly mess that up. One of the things that I suggest as a strategy to kind of avoid that and get repeatable things is to script what you're doing, either via IPython or using GDB script, which is just a file that has these exact same type of commands. It's just GDB will execute them in order. And so that allows you to have a fixed set of actions that should bear repeatable results. And so then you could run your script and be like, hey, this isn't showing what I think. I fix up my script. It's a lot more rigid process. My guess is that is what was occurring. As long as we're living over here, well, that isn't the stack, but we're dealing with stack locations, what I said is true. When you start getting to dynamic things, it's true, but then we have to have a great asterisk behind it and explain why. Any other questions about the current module? Anything that I didn't cover there? So something you're like, hey, I saw this, I didn't know what to do with it, I didn't know what it got me. I don't understand what PIE is, I don't understand what ASLR is. We're all good on all of that. Yeah? Cool. All right. With that, then I guess I can start looking at this 8086 emulator. We've got 15 minutes or so. Twitch. Twitch says, camera is not based on FaceTime. Is there going to be new challenges in this new module? So I had a slide earlier here. The answer is, as of tonight at 6 p.m., no. But I am considering it for like 7 days in. Like, I already know what would be there, but I'm not doing it here on day one. Okay. So do people have a strong opinion on what decompiler they use? Anyone like Ghidra, IDA, Binary Ninja? I don't care. Just show me something. All right. So objectively, the kind of consensus, the best tool is IDA. It tends to yield the easiest to understand C-like syntax. All of these are installed on the dojo. IDA is located up here. It's this little Mona Lisa looking icon. You may have used it already. I'm going to open up maybe this 8086 binary, and it gives me assembly. Now, the whole reason that you use a tool like this isn't necessarily to look at assembly, it's to look at some C-like syntax. To use IDA, the number one button you need to know is tab. Not an insanely complicated tool to use. That will lift up that assembly to some C-like syntax. However, there's a lot of information that's lost here. What is the name of this function? Where am I in this? What does it do? IDA doesn't know, right? We have to provide information to this tool to try and recover it and make it look like C syntax. Now, a brief aside, since I know that you're going to be doing this reverse engineering module here, there are 0.0 and 0.1 challenges. Very similar to what we had with the memory corruption. These are going to be the exact same type of challenge. Right? The same sub-problem exists. The 0.0 has symbols. Anyone know what that means?
Names for the functions.
Like names for the functions. Exactly. So if my personal advice to you, the first one you get here is 12. I think I'm going to spare you the 8086. I'd rather for today, 15 minutes, we're not going to get too far. I'd rather show you some tips and tricks for working on stuff that you're actually going to be dealing with here tonight. They're just in hindsight. if I open up 12.0 in IDA, my 8086 had unknown, we don't know what any variables are. If I open a 0.0 challenge, IDA is going to have function names. It's going to, again, just hitting tab, it's going to have function names. It's going to have things that make some sense and are maybe recognizable to you. Right? So this is a function in the Yon85 emulator. It's called sysopen. What does it do? Well, it calls open. Right? So this is a wrapper in the emulator. If the emulator needs to call open, it still needs to interact with the underlying x86 syscall open. Not particularly interesting. I can hit X if I want to cross-reference a symbol. So there's something I want to know, where is this all used in this whole binary? In this case, sysopen is called in one place. It is called right here. So I clicked on the symbol I was interested in. I hit X. It gave me a list. This was a list of one thing. I double-clicked on that one location. Okay, sysopen is called in wherever I am. What function am I in? I am in some function called interpret sys. Any guess on what this thing does? Again, an emulator is a program that needs to pretend it's a CPU, right? Or pretend that it's doing these operations. So somewhere in the CPU, and it's like made up architecture, it has to have something that's very similar to a syscall that you've seen in x86, right? And when we write AMD's, when we wrote shellcode, we had this syscall instruction. Yeah? Well, Yon85 has to have some similar abstraction. And so this is a function within Yon85 that interprets the Yon85 bytecode and then calls the corresponding x86 syscall. And so when we're looking at this, we want to be having that mental model of how does the CPU work? It has registers. How did we write assembly? Right? Instead of this emulator running x86 assembly, it's going to run Yon code assembly. What does Yon code assembly look like? I don't know. We got to reverse engineer this thing and find out. Look at the comparisons. Look at what is this function checking. This is something called interpret sys. If part of its input ends with 4, then we're going to call open. It's not worth writing this down. I'll let you know that working together on this particular set of challenges is a recipe for pain. There's a lot of small details of these binaries that are just randomized instances. So what I'm showing you here, 4, has something to do with opening. You open up yours, that could be 8, that could be 16, it could be some other number. All right. That's why your process of trying to understand what's going on is to open this thing up, read the pseudo-C, try and make sense of it. Now, have I found main yet? I just ended up at some random point of open, right? What if I want to know, where is this interpret sys thing done? I hit a button, I saw the motion. What was the button? X. Ooh, it says there are no references to interpret sys. We're doomed. It's all over. All right. So, in truth, the first couple challenges, try and be gentle. And what I mean when I say that is the first couple challenges aren't the full implementation of the Yon85 emulator. So this is some vestigial or like leftover implementation details of the true Yon85 emulator that isn't actually used is what I would go with. And so I did this like bottom-up approach. I started in open, I xref'd, and tried to get my way up to the top. But what is the beginning of execution of this thing? If I wanted to go top down, where do programs start running? Okay, there is underscore start. Underscore start is not particularly interesting because that's a little bit before the actual, what we consider the user land program fires up. It's a legit answer. But the program that we write in userland, that kind of begins at main, right? And so we could go on the left-hand side here, find main into a top-down approach to understand what's going on as well. It's whatever makes sense to you. And so we can see this thing prints out some nice help text. It says we're going to introduce you to this Yon 85 thing. It's a teaching challenge, which means it's going to output what this Yon 85 code looks like. It didn't print anything. It's not a good sign. I will take a look. I will take a look at that and see what's going on there. If that's an intention, if there is a bug with the printout or the lack of printout. Yes.
It prints the incorrect, right?
So it does print out the incorrect. It's not what I was expecting. If I'm going to be honest with you. Let me see if I did like 13 does what I'm expecting. Okay, so that does something closer to what I'm expecting. I'll take a look at 12.0 and announce on our Discord if there is something. Like I'll update the binaries for you if they should be. This is closer to what I was expecting. And so my recommendation to you is not to try and solve like 12.0 or not to try and solve, what is this, 13.0? But spend the night just looking at this thing in IDA and try and make sense of it. Stare at this output and try and make sense of it. All right. This isn't because level 12 is so daunting and scary. It's that every challenge is going to use this stuff. And so the earlier you take a look at this and internalize what it's representing, is that a hand or no?
Yeah.
Okay.
Sorry, finish the thought.
Okay, but the sooner you take a look at this and make sense of what it's displaying, the easier it will be to start cruising through all of the challenges.
Yeah, so my question is the idea to look at after this is outputted to us in GDB and see what instructions those correspond to?
So there's a number of ways to tackle it, and there's like this double abstraction to what we're doing here, right? I can run this thing under GDB, and if I wanted to, let's fini from here. It's a trick you've seen me do before. I disassemble. Here, I'm inside this execute program, right? I'm not looking at this dynamically, but what I'm looking at is the x86. What I'm debugging here is not the Yon 85. I'm debugging the x86 that is the emulator, right? So you can use both tools to reason about what's going on. My suggestion initially, and I love GDB, so it's a shame that I have to say this, but the right tool to probably get a high level understanding of what's going on is not going to be to delve into this thing in GDB, right? It's going to be to open it up in IDA and understand just a high level. Okay, there's main, and then what happens, right? It gets some bytes. What does it do? What does this run loop look like? This run loop is going to be very similar to your understanding of how an x86 CPU works. An x86 CPU, when we were doing shell coding, there was RIP. It pointed to somewhere. It interprets some bytes, it'd run it, it would increment to the next spot. There's going to be some type of similar abstraction here. Now, did you have a hand?
Yeah, I just want to ask, so is the architecture going to be consistent for these levels?
The question is the architecture consistent across these levels? Is the last one? I think so, yeah. So the instruction set is, I would say, right? So much like on x86, we have move, we have push, we have pop, right? These abstractions exist in Yon 85 architecture as well, right? Like add, that's a pretty universal term. What do you think this does? It adds two things. right? That's not too hard. What is this STM? Well, that you probably haven't seen before, right? It is actually an acronym for something. And if you look at either this or you look at how this is implemented in IDA, you should be like, okay, how does this relate to what I know about how a CPU works? IMM. It's not something we have directly in x86. We don't literally have IMM. But you could probably figure out what it's doing, right? Either from looking at this and reasoning about it, or by looking at an IDA and seeing, well, what happens when IMM is executed on this made-up CPU? So the actual made-up YON85 instructions will be consistent throughout the challenge, throughout the challenges. The encoding will not. I got a strange face there. I see the hand. Give me 1 sec. I don't want to respond to the face. So no. So when I say encoding, when we did the shell coding module, we could have our Python say ASM move REX hex 1337, right? And the bytes that were resulted from assembling that was consistent. I could assemble move REX hex 1337 500 times. It'll be the exact same bytes. The encoding will be different across every single one of these challenges. So it's what byte corresponds to like what opcode, right? That's what I mean when I say encoding. So there is consistency in what is the design of the instructions. There is inconsistency, which is something that you have to reverse and kind of, which is a bit tiresome. But from repetition, you'll get there. Quickly find it in the binary so that you know what the encoding is, yoink it out, and then use that knowledge. To your answer.
Yeah, so my question was, because I'm one of the people that did 365 a while ago,
Mm-hmm.
I forgot the format of these reverse engineering challenges. Is the idea to go through this like printed code and type the predicted output like at the end, or like in order like actually getting the flag as opposed to like understanding this?
So this is exactly the kind of question where I'm like, you got to reverse engineer it, right? Like if we read the help text here, you need to understand what this program is doing in order to understand how to get the flag, right? I believe this may be a bit of a spoiler here. The first like 12 or 13, the first couple, they are using this emulated CPU and like running their own thing. All right. For those that haven't taken 365 or it's been a long time, these earlier 12 or 24 levels are a crack me. Does everyone know what a crack me is? You give it some input, it's going to mutate it, XOR it, bit shift it, shuffle it around, and then you have to say, all right, here's what it is at the end, and work backwards to figure out what is the correct input to satisfy some constraints. All right? From memory here, the first couple of these YON85 challenges are essentially that, except now it is doing that on this YON85 CPU instead of an x86 CPU. And then later challenges, the 0.0 will prompt you, for instance, for YON85 bytecode. At which point now I need to go into look at the implementation of the emulator. I need to figure out what are the encodings. What is this? What do I want to execute on this made-up CPU, and how do I make this made-up CPU do it? Right? We saw when I first opened one of these up in IDA, there is, for instance, open. There is an ability to make this program call open. I imagine there's the ability to make this program call read. There's probably the ability to make it call write. But the question is, how do I do that, right? And you figure that out by reversing the binary. Now, when I say stare at these, stare at a 0.0, because the 0.0 has those names. They have symbols. The 0.1 binaries do not. So all of that nonsense of everything being unknown and messy is what you will experience every other challenge. And so my recommendation to you is to spend a lot of time staring at the very first 0.0 challenges until it makes sense to you how this thing works. Here I am in main again. We do see like libc functions are there, but then we get into sub whatever. Now I have this. What is this doing? Okay. The 0.0 and 0.1 challenges are functionally the same thing at a high level. Spend your time staring at the 0.0 challenges, so then when you look at something like this, I want to know what is this thing right here. I can look at that and I'm like, hey, I've seen this pattern before because I saw it in the 0.0 challenge where it had a name. Reverse engineering is about a few things: high-level reasoning, pattern recognition. Don't go down the rabbit hole of running something in GDB and trying to read assembly one line after the other, after the other, after the other. I can't do that, and I like assembly, right? That is just way too much time being spent. Identify high-level patterns from the 0.0, use that to inform you about what's going on in the 0.1. On Thursday, I plan on spending most of the class time going through like this type of process where I don't know how do I make this look more C-like. Inside IDA, you can change, or any of these decompilers, you can rename this variable. I could type it. Maybe it thinks it's a char, but it's actually an int. These tools are imperfect. They will lie to you. And so it is your job to correct it when it makes a mistake. And you could spend a long time changing and renaming these things every challenge, or you can stare at the 0.0, identify the patterns. So then when you look at the 0.1, I don't have to rename it because I've seen this before. And so I'm spending less time on this tool and more time getting flags. Any questions? Because I am over time. Yes?
I want to solve the previous model challenge, but is it worth for the grades to solve it?
The question is, I want to solve the previous module's challenges. Is it worth it for the grades? So the answer is it doesn't matter whether you solve any of the late stuff today or you solve it during finals week. It is worth 50% credit at any point. Your highest value action for your grade is always going to be to work on the current challenges. And so definitely at least to the checkpoint, right? Because that's got that extra, the first half. So if you are trying to optimize for your grade, your time is best spent solving half of what's getting thrown at you now, at least, before circling back. It is worth it for the grade. So one of the questions on the on-topic in-class Discord channel was, hey, I got like a 60. You know, I don't know who asked it, right? And you know, can I still get an A+? Hey, what does this math look like if I solve everything late? And I didn't know the answer. And so we did the math. And if you got I think it was 61 was the literal number. If you got a 61 on every single module and then solved the rest late, with all of the extra credit, you could walk out of here with a 97, I think it was. Okay?
61 on every single module?
A 61% on every single module for the entire course, but you solved everything late. You solved the remainder of them late. That wasn't a scenario I had in my slides. It was a totally fair question. And so that's where I want to be very transparent about the grades, but I want people to also be able to put that in context, right? You have the ability to solve things late until the end of the semester. You have that extra credit. It will help you. But if you are really, really struggling with the course, I try and make the best choice for you. All right. Twitch chat. What is the program asking for? Well, that'll be a mystery. You got to reverse it. So with that, we will leave you there. I appreciate everyone hanging out. I will see you on Thursday.